Hi, my name is Joe Kelly. I worked with Jay Shankur on the project of testing robustness of scale-free networks for our final project with network science. What we looked at was that many networks, internet, biological, and social networks, show that they have a scale-free property where their probability of having a degree followed an exponential function with the exponent of gamma being between 2 and 3. Barabasi argues that a scale-free network is robust, but we wanted to know exactly how robust they were and what different attack vectors would make them more vulnerable than others. We wanted to test scale-free networks on a number of different measures in order to find this out. We looked at a few resources to find what literature existed for network robustness. Iyer, Kilback, Sandrum, and Wang in 2013 did an analysis that looked at attack based on degree and other centrality measures. The measure of this was based on the giant component. And in this case, the Iyer et al. Paper is different from some of the Barabasi work that we studied in this class, where the attack was always based on the degree. This expands it to other centrality measures. We try to verify those results and extend them. Barabasi in 2016 discussed the Molloy-Reed criteria as a different measure of network robustness, where the second moment over the first moment is greater than 2, and that means that the network is intact. So we wanted to also extend this work by looking at the Molloy-Reed criteria for the different measures. So our motivation is, are scale-free networks robust against random and targeted attacks? Which one are they more vulnerable to, random or targeted? And which particular type of targeted attack is better or worse for robustness? And will robustness help slow down the propagation of diseases and viruses? Our hypothesis was that scale-free networks are vulnerable to attacks and spreading viruses. A malicious attack will disintegrate the scale-free network. Those are our two hypotheses that we try to prove here. There are the robustness tests of the Iyer, Kilback, Sandrum, and Wang, where we attack railroad networks of the drug network, drug protein network, and internet networks. Try to verify those findings, and again, we're applying the Molloy-Reed robustness as it relates to the giant component robustness analysis. Insofar as methods and variants, you can remove nodes on a number of different ways. You can randomly remove whatever node you want to. In the literature, that's kind of referred to as a failure, that you have a set of computers and one randomly fails. That happens at random. It's a failure. Now, there's different ways you can attack a network. If you're evildoer and want to do harm to a network, or if you want to disrupt a bad cell that's got cancer for some reason, you can attack it based on the degree of the network. Or these other measures that we discussed in class, betweeness, closeness, and eigenvector. Those are all other ways of measuring the most important node in a network. In addition, there are a couple of variants in terms of that. You can either look at the very initial graph and say you want to attack 20 nodes. You can look at the initial graph and say, here's the most important 20 nodes, and attack those one by one. The other way is to do something with recalculation. That is, you take the initial graph, you find the most important node using whatever centrality measure, you remove that, you recalculate the centrality measure, you remove the next node, you recalculate that, you remove the next centrality, the next node, and so on and so forth. It's a little bit slower process because there's more recalculation involved, but it may be real world in the case of the drug or protein network, where one cell exists, carries a mutation for some reason, goes on to another generation, and then you remove something else and it continues on for another generation, and so on and so forth, where that would just naturally occur. So we did find that there was a significant difference between these two variants of the initial graph or the recalculation turned on. Well, what are we measuring? We can measure the percent of the giant component or the Molloy-Reed criteria. What graphs did we use? We used the drug protein network. As we mentioned, the internet is another network that we used, and we measured a scale-free network, hypothetical scale-free network that we used network X in order to calculate for us. In terms of our results and discussions, we found that the networks were quite robust in terms of random attack, especially for gamma less than 3. The removing of the nodes did not break the network down into islands. The critical point we chose was that 1% of the giant component was left over. And in order to get to that point, we would really have to randomly remove 92% of the nodes. These solid lines represent the solid bars of the drug network, internet network, and scale-free network. And all those are very robust, like I say, down to about 92%. The dotted lines are the targeted attacks. And with those, if you remove about 10, 15%, you really do disrupt the network quite a bit. It's a very steep slope down there, and these nodes, these attacks are quite effective. This is looking at the degree attack. Now, here we attack it in multiple different ways: betweenness, closeness, degree, eigenvector, and random attack. Here we see with the random attack, you're quite robust. You're not disrupting the network very much. And here the scale-free network, this is, by the way, with recalculation turned on. That is that after every instance of the graph has a node removed, you recalculate the measure and then find the most important node and then remove that. So with recalculation turned on, with the scale-free network, they all perform pretty well. They're all pretty well in the same range and disrupting maybe less than 10% of the nodes really disrupts the whole network. With this real-world network of the drug protein, we see there's a little bit of differentiation. The red and the blue are betweenness and closeness, and those are less robust than the green and black of degree and eigenvector. Now, if you're trying to attack a network, then we would recommend that you do betweenness or closeness in order to get the most effective, quickest reduction in the network. If you're really hoping that your network is not going to be attacked, it would be probably good if someone is choosing to attack you with eigenvector or degree, as that's not quite as effective. It buys you a little bit of extra time there. They would have to attack, 5% more nodes in order to really disrupt your network. Here we're looking at when we don't have the recalculation turned on. That is that we base all our decisions based off of the very initial graph. So the very initial graph says, here's what centrality looks like for closeness. Here's what the betweenness looks like. Here's what the eigenvector looks like. And based on that very initial graph, you remove the 20% of the most important nodes. And when you do that, with either the betweenness or degree attack, that is pretty effective. Removes all the necessary components to very well disrupt the network. Whereas if you do that with closeness or eigenvector, it is not exactly as effective. You really have to remove 40-60% in order to disrupt the network. Again, with the scale-free network, the results aren't quite as dramatic, but still we see the trend that eigenvector and closeness are not as effective at disrupting the network. They are ways that if you're attacking a network, it would be more robust to those types of attacks. Here with the Molloy-Reed criteria, we really look at the number 2. That's the criteria upon which the network is no longer intact, whereas before that point it is intact. We see that this drops quite significantly in most cases, and it disrupts around the 10% mark for everything. The solid lines are where recalculation is true, and the dotted lines are where recalculation is false. Now we see here that with the closeness that we have to disrupt about 40% in order to see a real disruption of the scale-free network, in this case, in order to disrupt the network. We see that's consistent over here, where we have to disrupt about 40% of the scale-free network in order to disable it. Whereas with eigenvector, we see that that line goes down here about 20%, 40%, and we still have a little bit of the network. We're more than 1% at this point. But with eigenvector down here, we see about a 10% figure for the Molloy-Reed criteria. So that would mean that 10% is about here, that the Molloy-Reed criteria is saying that this eigenvector network is disabled at this point, whereas based on the giant component, it's still very much intact. So these are different measures. They measure different things, and they produce different results. It is interesting that they are somewhat not in sync, given that they both are trying to measure robustness. So we found that to be quite interesting. One of the big challenges with this project is simply the amount of time that it took. Jay was very efficient at coding the project and got that done pretty quickly, but it took a computer a lot of time to process it. Even with GPU processes enabled, it took us several days to run through this. Now, we may not have come up with the most efficient code in the first place, and there may be ways that we could do faster computations. We could compile this code somehow by using a different language or something else. And our conclusions at the end of the day are, of course, that the Molloy-Reed and percent of giant component are not correlated exactly. We saw that on the very last slide. The scale-free networks are robust against random attack. We saw that with the lines that were quite different from the target attacks, where we have to, like we say, disrupt about 92% of the nodes in order to really disrupt the network. And we saw that diseases, viruses, and contagion are spread mostly at random in the real world, and therefore scale-free networks would be naturally robust against failure with regard to those measures. We looked at a few journal articles, of course, to make sense of this. Here are some of them. Here are some more. Overall, we both really enjoyed this class, and here's the end of our presentation. So we hope you enjoyed this class as much as we did.